Greetings and welcome back, math people of YouTube. Your boy Kamal here with yet another very interesting integral. We have the integral from 0 to infinity of log square x divided by x squared minus x plus 1. And the solution development is really cool, and we're going to derive a related result later on in the video. So how exactly would I like to begin? Well, I'm actually going to define an integral function, I of some parameter alpha, as the integral from 0 to infinity of x to the alpha divided by x squared minus x plus 1 dx. And the reason for that is if we differentiate I with respect to alpha, we get the integral from 0 to infinity of the partial derivative with respect to alpha of x to the alpha divided by x squared minus x plus 1 dx. And on differentiating, we get the integral from 0 to infinity of x to the alpha times log x, because we're differentiating partially with respect to alpha. So we have x here held as a constant for differentiation purposes. Then we have x squared minus x plus 1 in the denominator. Now, notice that if we differentiate this thing one more time, we get the second derivative of I with respect to alpha equal to the integral from 0 to infinity, terribly sorry about that, of x to the alpha times log square x divided by x squared plus x minus 1 dx, meaning that the target integral is actually just the case of alpha being equal to 0 for the second derivative of the integral function. Okay, cool, but for our plan to work, we need to get a closed form for our integral function, which is not exactly a very difficult thing to do. The integral function is actually quite friendly relative to the actual target integral. So to solve it, for closed form in terms of alpha, we're going to expand the integrand using x plus 1. So we have the integral from 0 to infinity of x to the alpha divided by x squared minus x plus 1 times x plus 1 divided by x plus 1 dx. Now notice in the denominator on multiplying terms, we get x cubed plus 1, and in the numerator, we have x to the alpha plus 1, terribly sorry about that, plus x to the alpha. And now using the linearity of the integration operator, I now have two integrals to evaluate. So we have the integral from 0 to infinity of x to the alpha plus 1 divided by x cubed plus 1 dx, plus another integral from 0 to infinity of x to the alpha divided by x cubed plus 1 dx. So we're going to call this one here I sub 1, and this one's going to be called I sub 2. And now we have to evaluate these two very cool looking integrals, and we'll do that by making use of a very special function. Wait, before applying any special functions, we need to transform the integral slightly. And by slightly, I mean letting x cubed equal u, which implies that x here equals u to the 1/3, and this further implies on differentiation that dx equals 1/3 times u to the negative 2/3 du. And the limits of integration are not affected by our transformation. Okay, cool. So this implies that the target integral, or rather the integral function I of alpha, equals 1/3 of the integral from 0 to infinity, and we had x to the alpha plus 1. So that means we have u to the alpha plus 1 divided by 3 times u to the negative 2/3, terribly sorry about that, du divided by 1 plus u, plus 1/3 of the integral from 0 to infinity of u to the alpha by 3, because we had x to the alpha, and we have u to the negative 2/3 divided by 1 plus u du. So some simplification is in order. We have 1/3 of the integral from 0 to infinity of u to the alpha minus 1 by 3 du divided by 1 plus u, plus 1/3 of the integral from 0 to infinity of u to the alpha minus 2 by 3 divided by 1 plus u du. And the very special function I was talking about is the gamma function. Specifically, we're going to use the integral representation of the reflection formula for the gamma function, which can be derived quite easily using the integral representation of the beta function and its relation to the gamma function. I've done it numerous times here on the channel. Anyway, so what exactly is that integral? It's the integral from 0 to infinity of x to the s minus 1 divided by 1 plus x dx or du, whatever, you can name the dummy variable anything you want. This is supposed to equal gamma s times gamma 1 minus s. So in our case, for the integral I sub 1, that's this thing here. This thing was I sub 2. So for I sub 1, we have alpha minus 1 by 3 equal to s minus 1, which implies that s equals alpha by 3 plus 2/3, correct? Okay, cool. And for I sub 2, we have s minus 1 equal to alpha by 3 minus 2/3, which implies that s here equals alpha by 3 plus 1/3. So this implies that the integral function I of alpha equals 1/3 of gamma. Wait, I'm just going to write this directly. We know what the gamma function times gamma 1 minus s equals. That's supposed to equal pi by sine of pi times s, or pi times the cosecant of pi times s by the reflection formula. So that means we're left in the first case, for the case of the first integral, with pi by 3 times the cosecant of pi times, okay, so we have pi alpha by 3 plus 2 pi by 3 plus pi by 3 times the cosecant of pi alpha by 3 plus pi by 3. Okay, cool. And by the way, if anyone's looking for a proof video on the reflection formula, link in the description below. So that's I of alpha. Now we have to differentiate it a couple of times, which is kind of annoying, so I'm just going to snap my fingers. Hey, what do you know? Those infinity stones really do work. Anyway, so this is what we get for the second derivative of the integral function with respect to alpha. But we were interested in the case of alpha being equal to 0. So in that case, we have our target integral I equal to I double prime at 0 equal to pi cubed by 27 times, what exactly are we getting here? We have 1 by sine cubed 2 pi by 3 plus cotangent square, might as well write this as 1 by tangent, whatever, doesn't matter. 1 by tangent squared, you know what, let's make this less clunky. 2 pi by 3 plus cotangent squared 2 pi by 3 times cosecant squared. No, it's just cosecant 2 pi by 3 plus we have cosecant cubed pi by 3, and the same thing as in the above line for pi by 3. Okay, cool. And all you have to do is plug in the values and perform some simplification. And we finally get the result of the target integral being equal to, wait, I've noted this down. Yeah, it's 20 pi cubed divided by 81 times root 3. Okay, cool. That's a nice looking result. I mean, we have the numbers 20 and 81 making their debut here on the channel. But I said something about a related result. Well, there is a nice integral that's quite similar to our integral. It's the integral from 0 to 1 of log square x divided by x squared minus x plus 1 dx. And let's call this one j for a change. So we can relate I to j using a nice transformation. So I here is the integral from 0 to infinity of log square x blah blah blah. We can write this as the integral from 0 to 1 plus the integral from 1 to infinity of log square x divided by x squared minus x plus 1 dx. And for this integral here, we perform the transformation x to the 1 by x realm, which takes dx to negative 1 by x squared dx, and the limits would be 1 and 0 now. So that means for this integral, we have the integral from 1 to 0 now of log square 1 by x divided by 1 by x squared, terribly sorry about that, minus 1 by x plus 1, and the differential element is now negative 1 by x squared dx. So Switching up the limits of integration gets rid of the extra negative sign, so we now have integral 0 to 1. And what about log square x? Log 1 by x is equal to negative log x, but here we're squaring everything, so we still get log square x. So there's log square x, and in the denominator, what exactly are we getting? We're getting 1 minus x plus x squared divided by x squared, 1 by x squared here. Some nice cancellation, meaning that this integral equals the integral from 0 to 1 of log square x divided by x squared minus x plus 1 dx, which is exactly what this thing equals. So that means I equals 2 times the integral j, and this implies that the integral from 0 to 1 of log square x divided by x squared minus x plus 1 dx equals half of the result we just derived, which sorts out to 10 pi cubed divided by 81 times root 3. Again, a very nice result, and I believe this is the first time I ever saw 10 as the result of one of my integrals, which makes this video a perfect 10, I believe so, which is good enough to warrant a like and a subscription to the channel. I hope you enjoyed the video. Be sure to like and subscribe, and more importantly, I hope you learned something from the video. Do drop me a follow on Instagram as well, and in case you like the content I'm putting out, in case you're learning something, consider supporting my efforts on Patreon. Thank you. See you next time.